The topic of today's lecture is topological quantum computing, and we will begin with a discussion of the quantum Hall effect. So what is the quantum Hall effect? So this is the phenomena that occurs in two-dimensional electron fluids. So this means that we have free electrons that can move inside a two-dimensional film in strong magnetic fields. So this means that we immerse this electron fluid in a strong magnetic field that goes perpendicularly to this surface of this film. And all this happens at low temperatures. Quantum energy states of electrons in these settings were computed by Lev Landau, who showed that the energy states are equally spaced, and when we increase the strength of the ambient magnetic field, the spacing between energy levels increases. So these energy levels become located further apart. And moreover, not only the spacing between the energy levels increasing, but the energy levels themselves become wider. So this means that at stronger magnetic fields, more electrons may occupy the same energy level. As a result, when the ambient magnetic field is relatively weak, then more of these energy levels are filled. And when the magnetic field gets stronger, then the filling number, so the number of field levels, decreases. So this filling number need not be an integer. So for example, we could have nu equals 4.5. So this would mean that 4 energy levels, 4 Landau levels, are filled completely, and the 5th energy level is only half full. Or, so at stronger magnetic fields in the same system, we could have the filling number being equal to 2. So this means that now we have more electrons per energy level, and we could have a situation when in the same physical sample, only 2 Landau levels are filled completely. The quantum Hall effect is the quantum anomaly that affects the behavior of currents inside this electron fluid. The ambient magnetic field, which is perpendicular to the plane of the fluid, will affect the trajectories of the electrons. As a result, the usual Ohm's law, which says that the current is equal to voltage divided by resistance, this law will become tricky in this setting because the direction of the current is no longer the same as the direction of the applied voltage. And in this setting, we will need to write the Ohm's law in vector form. So the vector of current, and this is a two-dimensional vector because we are looking at the two-dimensional fluid of electrons, is equal to the inverse of the resistance matrix. And the peculiarity here is that resistance now has a matrix form times the voltage vector, U1, U2. Here, the diagonal entries in the resistance matrix, ρ1 and ρ4, which are equal to each other, are called longitudinal resistivity. and the absolute values of off-diagonal elements, row 2 and row 3, which are also equal, are called transversal resistivity. In the classical Ohm's law, so we only have longitudinal resistivity, and the transversal resistivity is equal to 0. When longitudinal and transversal resistivities are measured at different strengths of the ambient magnetic field, clear quantum effects emerge in the picture. The following graph from the Wikipedia page on the quantum Hall effect plots the longitudinal and transversal resistivities at different strengths of the magnetic field. Here, the blue line shows the longitudinal resistivity, and the brown line shows the transversal resistivity. In this graph, we observe clear quantum effects at integer values of the filling number. However, there are also more subtle quantum anomalies that occur at fractional values of the filling number. So, for example, when the filling number is exactly half integer. The latter case is known as the fractional quantum Hall effect. The exact mechanism of the quantum Hall effect is still not understood. However, the existing models predict that quasiparticles form at the special values of the filling numbers. There are indications that for the fractional Hall effect, the quasiparticles that emerge there have anyonic nature. Thus, the fractional quantum Hall effect is the most promising physical setting where we can hope to discover anyon quasiparticles. This means that these quasiparticles will acquire an additional phase factor when we move one quasiparticle around another. Alexei Kitaev proposed to use anyons for topological quantum computing. The quantum memory of such a computer will be realized as an ensemble of several quasiparticles, and computations are performed by moving these quasiparticles around each other. What's important here is that the operations on the quantum states are topological in their nature. So they only depend on the homotopy type or the topological class of these trajectories. And the result is not affected by small perturbations in these trajectories. For example, we take one of the quasiparticles and move it around the other two. The outcome of this operation will be exactly the same if we use a different trajectory in the same topological class. This feature of topological quantum computing makes it extremely attractive because accumulation of errors creates a lot of problems for engineering implementations of the conventional quantum computing. Let us see how topological quantum computing works using a specific example of anyons called Fibonacci anyons. Fibonacci anyons may be occurring in fractional quantum Hall effect at the filling number nu, which is 12/5. In this theory, we have two quasiparticles, or two types of quasiparticles. One which is denoted by tau, so this is the Fibonacci anyon. And the second one, which is denoted by 1, so this is the trivial anyon. And it's essentially vacuum. When we move two quasiparticles together, they may fuse, forming a more elementary system of quasiparticles. And this process is described by something which is called fusion rules. So these fusion rules are that when we fuse the trivial quasiparticle with itself, then we get the trivial quasiparticle. When we fuse the trivial quasiparticle with the Fibonacci anyon in either order, and the fusion rules are commutative, so we get the Fibonacci anyon. And finally, when we fuse the Fibonacci anyon with another Fibonacci anyon, then here the outcome is more interesting. So here the result is the expression tau plus 1. This means that we have two possible outcomes of fusion of two Fibonacci anyons. We may either get a single Fibonacci anyon, or we may get the trivial particle 1. The fusion rules yield an associative commutative algebra. Which is two-dimensional, and it has two basis vectors, a unit 1 and a generator tau. Let us see what will happen if we fuse three Fibonacci anyons. So we compute tau times tau times tau. So in this case, this is tau times tau plus 1. So tau times tau is tau plus 1, and tau times 1 is tau. So the result is 2 tau plus 1. If we take the product of 4 Fibonacci anyons, so this is tau times 2 tau plus 1. So the first summand will be 2 tau plus 2, and then plus tau. So we get 3 tau plus 2. If we take a product of 5 Fibonacci anyons, then this is tau times 3 tau plus 2. And here we get 3 tau plus 3 plus 2 tau. So this is 5 tau plus 3. At the next step, we will get tau times 5 tau plus 3. So this will be 5 tau plus 5 plus 3 tau. And so this is 8 tau plus 5. Now we can see what's the pattern in this computation. And we see that these right-hand sides are of the form n plus first Fibonacci number times tau plus the nth Fibonacci number. These coefficients 1, 1, 2, 3, 5, 8 is a very well-known Fibonacci sequence, where the formula for fn plus 1 is the sum of fn and fn minus 1. Let us issue a warning. The result of a computation in the fusion algebra does not give the number of quasiparticles obtained as a result of fusion of n Fibonacci anyons, but rather counts the number of fusion channels. For example, this computation says that when we fuse together 6 Fibonacci anyons, then as a result, we can get either a single Fibonacci anyon or the trivial particle. And there are 8 channels in which 6 Fibonacci anyons fuse to a single Fibonacci anyon. And there are 5 channels in which 6 Fibonacci anyons fuse to a single trivial particle. Let us look at our basic fusion rule. Tau times tau is equal to tau plus 1. So this means that when we take a pair of Fibonacci anyons, may exist in 2 states. So a state where 2 Fibonacci anyons fuse to a Fibonacci anyon, and a different state where a pair of 2 Fibonacci anyons fuse to a trivial particle. So effectively, the fusion algebra counts the number of states of an ensemble of n anyons. Then the general state of a pair of Fibonacci anyons can be written as alpha times tau tau producing tau plus beta with a channel where this fusion of 2 Fibonacci anyons produce a vacuum. So that is the annihilate. With the condition, of course, that alpha and beta are complex numbers, and norm of alpha squared plus norm of beta squared is equal to 1. Let us list the basis states of an ensemble of 3 Fibonacci anyons. Here we could have, so we start with 2 anyons. So 2 anyons may fuse to tau, and when we fuse it with a third anyon, we can get tau as well. So then we could have a possibility that 2 Fibonacci anyons fuse to 1, and when we fuse it with tau, 1 fused with tau is always tau. So here we must have a tau. And the final case is when we have 2 Fibonacci anyons that fuse to tau, and when we fuse it with the third Fibonacci anyons, we get annihilation and we get a trivial quasiparticle. So if we recall our fusion rule, so tau times tau times tau was equal to 2 tau plus 1. So this tells us that there are 2 fusion channels that lead to forming of the tau anyon, and a single fusion channel that leads to the trivial quasiparticle. Now let us do it for n equals 4. So the product of 4 tau anyons in the fusion algebra is 3 tau plus 2. Now we take the fusion states of 3 Fibonacci anyons and fuse them with an additional anyon. So let us list the states where the outcome is tau. So here we have tau times tau leading to tau times tau leading to tau times tau and the outcome is tau again, then if we take the second state, which leads to tau, and we fuse it with tau, we also may get tau. And if we take the third state, then we can get tau as well. So when we fuse 3 Fibonacci anyons in this channel, we get a 1, but when we fuse 1 with a tau, we must get a tau. Now let us list the fusion channels that lead to a 1. So the first 2 states, when we fuse them with tau, we may get a 1. So we have tau times tau giving tau, fusing with tau, obtaining tau, and fusing with 1 more tau, and the outcome of fusing 2 tau anyons could be a 1. And the same for the second state. So tau times tau fusing to 1, and then with tau fusing to tau, we fuse with another tau, we can get 1. But the last state, when we fuse it with another tau, we are guaranteed to get a tau, so we cannot get a 1. So this means that in total, we have 3 fusion channels that lead to a tau, and 2 fusion channels that lead to a 1. And that's exactly what the right-hand side in the fusion algebra is telling us. So there are 3 fusion channels leading to tau, and 2 fusion channels leading to a 1. And the conclusion is that an ensemble of 4 Fibonacci anyons has a 5-dimensional space of states. And the basis vectors in this space of states is different fusion channels. We point out that in description of this basis, we fix a particular fusion order. So first we fuse 2 anyons on the left, and then we fuse it with a third anyon. And the same here. So the fusion process goes from left to right. What will happen if we change the fusion order? Remarkably, it turns out that changing the fusion order produces a non-associative result. So in particular, if we take tau times tau leading to tau with tau leading to tau, so this state is not the same as the state where we fuse these particles from right to left. Instead, what we have is we have a second basis in the same space of states of 3 Fibonacci anyons. So what we could have is we could have basis vectors. So tau times tau times tau, tau leading to tau. We could have, if we fuse the 2 particles on the right leading to annihilation and then multiplied by the particle on the left, producing a tau. And finally, we could have a state where we have 2 Fibonacci anyons fusing to tau and fusing with tau again and producing the trivial quasiparticle. This will be a different basis in the same 3-dimensional space spanned by these channels. And we have the transition formulas that connect the first basis with the second. So in particular, so if we take a basis vector in the first basis, so tau times tau leading to 1, and then with tau leading to tau, so then this is the following linear combination. So this is phi to the -1 times tau times tau tau leading to 1 and then leading to tau, plus phi to the negative 1/2 tau times tau tau leading to tau and then leading to tau. The number phi that we use here is square root of 5 plus 1 divided by 2. So this is the golden section. For the other basis vectors, the transition formulas are like this. So if we have tau times tau leading to tau times tau leading to tau, so this is equal to phi to the negative 1/2 tau times tau tau leading to 1 and then leading to tau, minus phi to the negative 1 tau times tau tau leading to tau and leading to tau again. We see that the mixing of states is only allowed when the final quasiparticle is the same on the left and on the right. So the space of states has two sectors: a subspace where the fusion of 3 tau anyons leads to a tau, and the subspace where the fusion of 3 quasiparticle leads to the trivial quasiparticle. And the change of coordinates happens separately in each of these subspaces. Here, the subspace of fusion of 3 tau particles to a 1 is one-dimensional. So here we obtain the trivial formula that tau times tau leading to tau and fused with tau leading to 1 is equal to tau fused with tau and tau leading to tau leading to 1. So these two states are just equal. Let us point out that these change of basis formulas may be encoded with a 2x2 matrix, which is denoted by F. And so this is the matrix of the coefficients. So phi inverse, phi to the negative 1/2, phi to the negative 1/2, and negative phi inverse. And this matrix has a remarkable property that the inverse of this matrix is itself. So this means that if we want to transition from the right balanced basis to the left balanced basis, then we essentially use exactly the same formulas. When doing calculations with Fibonacci anyons, it's important to remember that the golden ratio has the following well-known property, that 1 plus phi is equal to phi squared. This change of basis formulas may be generalized in the following way. So let x tau, y tau, and z tau be 3 fusion channels resulting in a tau anyon. For example, so x tau could be tau times tau leading to tau. Y tau could be tau times tau tau leading to 1 and then leading to tau, and so on. Then this change of basis formulas may be generalized as follows. So if we have x tau times y tau fusing to 1, and this is fused with the channel z tau, resulting in a tau, so this will be equal to phi inverse times x tau fused with y tau and z tau leading to 1 and then leading to tau, plus phi to the negative 1/2, and we have x tau fused with y tau and z tau leading to tau, and then leading to tau, and so on. And so the same for the second formula as well. The change of basis formulas for triple fusion, including the vacuum, are all trivial. So, for example, if we have 1 tau and we fuse this with tau, then the outcome of the first fusion could be only tau, and suppose the outcome of the second fusion is 1. Then how can we rewrite this as a right order state? So here, if we have tau times tau, right, and then we fuse this with 1. So the outcome must be a 1, so that we are in the same sector. And then the only possibility for 1 fusing with the outcome of this fusion is when this outcome is equal to 1. If the outcome of fusion on the right is equal to tau, then the overall outcome of 1 times tau will be tau. And if the outcome of the fusion of the particles of the same type is tau, then here we must have, so 1 times tau times tau. So here we have to have the outcome of tau to obtain the same outcome as we have on the left. This change of basis formulas allow us to change the fusion order. And we point out that if we have a basis state in one fusion order, so that is, we have a fusion channel with prescribed outcomes on each step, then if we change the order of fusion of the quasiparticles, then the resulting state will no longer be a basis state. So it will be a linear combination of basis states. This means that by changing the order of fusion, we might go from a state where the outcomes of fusion on each step was deterministic to a state where the outcomes of fusion on intermediate states will be known only probabilistically. But we point out that the final outcome of the fusion process is independent on the fusion order. An operation which is crucial for topological quantum computing is interchanging two anyons, or also known as braiding. Let us discuss this operation. Clockwise exchange of two anyons introduces a phase shift to their state, but the value of this phase shift depends on the fusion channel of this pair of anyons. If we have a pair of Fibonacci anyons that fuse to 1, and we perform this clockwise exchange, then their wave function is multiplied by e to the 4 pi I over 5. Whereas if a pair of Fibonacci anyons fuse to tau, then this state experiences a phase shift with the factor e to the minus 3 pi I over 5. So if we have a pair of anyons in a superposition state, alpha times tau tau 1 plus beta tau tau fusing to tau, and we perform this clockwise exchange of these anyons, then the resulting state will be alpha times e to the 4 pi I over 5 tau tau 1 plus beta times e to the minus 3 pi I over 5 tau tau fusing to tau. Next, let us discuss how we can be making qubits with Fibonacci anyons. So this is rather tricky because the dimensions of the spaces of states of Fibonacci anyons are given by a sequence of Fibonacci numbers. And this sequence is not very well compatible with the powers of 2 that is in the foundations of our binary logic. As a result, when we'll be translating from binary qubits into Fibonacci anyons, there will be some redundancy left. In order to implement an n-qubit space, which has dimension 2 to the power n, we have to find the Fibonacci number that exceeds 2 to the power n, and somehow embed the 2 to the power n dimensional space of qubits into the Fn dimensional space of the Fibonacci anyons. We point out that the Fibonacci sequence grows exponentially with the exponent, which is the golden ratio, which has value just below 2. An obvious candidate for a single qubit is this composite state of a pair of Fibonacci anyons. However, it turns out that this is not the most appropriate choice to represent a single qubit. The reason is that the only operation that we can perform on a pair of anyons is braiding. And the braiding operation is given by a diagonal matrix R, which is e to the 4 pi I over 5, 0, 0, e to the minus 3 pi I over 5. And thus, if we iterate this, the result will always be a diagonal matrix. And in this way, we will not be able to generate arbitrary unitary operations on this two-dimensional space. To overcome this issue, we will be using joint states of a triple of Fibonacci anyons. And 0 qubit will be represented as tau times tau fusing to 1 with tau fusing to tau. Then 1 will be tau with tau fusing to tau, and then with tau fusing to tau. And then there is a redundant third state, which is denoted by n. And here we will have two leftmost anyons fusing to tau. And then when we fuse it to tau, this produces vacuum anyon 1. We point out that the two states that we're interested in will fuse at the end to the tau anyon, and the third redundant state, which is also called non-computational state. This state will fuse to vacuum. Now that we have a triple of anyons, let us see what will be the effect of the clockwise exchange of the two anyons on the left. Here, if we start with a 0 state, and then we are performing the braiding on the left pair of anyons, the left pair is in channel 1. This means that when we perform the braiding on this pair, the phase shift factor is e to the 4 pi I over 5. So this means that the 0 state will be multiplied by e to the 4 pi I over 5 times itself. Then the 1 state, in the 1 state, we have the leftmost pair in the tau channel. And this is braided with the phase shift factor of e to the minus 3 pi I over 5 times 1. And what will happen to the non-computational state? So in the non-computational state, the two leftmost tau anyons are in the tau channel. So this means that the non-computational state will also acquire the factor of e to the minus 3 pi I over 5 if we perform a clockwise exchange on the leftmost pair of the anyons in this triple. Next, let us see how in this triple can we braid two anyons on the right, and what will be the effect of this operation on the qubits. The difficulty here is that in these basis vectors, the two anyons on the right are not immediately fused together. And thus, in order to know how to braid the two anyons on the right, we need to transform from the left-normed expressions to the right-normed expressions. And we know that we can do this using the change of basis matrix F. So if we start with our zero state, which is written there, so it's tau tau fusing to 1, and then with tau fusing to tau, what we do is we first perform the change of basis. So we go to a right-normed basis. So this is by that matrix, so this is phi inverse times tau fused with tau tau in channel 1, and with the result tau, plus phi to the negative 1/2 tau times tau tau in channel tau fused to tau. Next, we apply braiding to the right pair of anyons. And so now the right pair of anyons is together. And we know that when we have a pair of anyons in channel 1, then this, after the braiding, acquires a phase shift of e to the 4 pi I over 5. So here we will get phi inverse times e to the 4 pi I over 5 times the same right normed state tau times tau tau 1 tau, and plus phi to the negative 1/2 times e to the minus 3 pi I over 5 times the state tau times tau 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 and tau. And now that we perform the braiding, we go back to our original basis. And to go back to the original basis, again, we use matrix F. So the above equals to phi inverse e to the 4 pi I over 5 times phi inverse, and then the state tau tau 1 tau, plus phi inverse e to the 4 pi I over 5 times phi to the negative 1/2 tau 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 times tau tau. And then we expand the second term. So we have plus phi to the negative 1/2 e to the minus 3 pi I over 5 times phi to the negative 1/2 tau tau 1 tau tau, and the minus phi to the negative 1/2 e to the minus 3 pi I over 5 times phi inverse tau 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 with tau. So now, if we denote by B12 the braiding of the first and second anyon, and by B23 the braiding of the second and the third anyon, then we conclude that B23 applied to the zero state is equal to, so now we combine these two terms together, right? So because, and this is the zero state of the anyon, so we get the coefficient at the zero state will be phi to the negative 2 e to the 4 pi I over 5 plus phi to the negative 1 e to the minus 3 pi I over 5, and this is times the zero state, plus phi to the negative 3/2 times, here we have exponential of 4 pi I over 5, And here we still have phi to the negative 3/2, and with a minus sign, exponential of minus 3 pi I over 5 times 1. So we see that the braiding operation of the two anyons on the right applied to the 0 state will produce a linear combination of the 0 state and the 1 state. In a similar way, we can compute the result of braiding applied to the 1 state and to the non-computational state. And we point out that the 1 state can only mix with the 0 state, but cannot mix with a non-computational state. This is because when we apply the change of basis matrix, then the two computational states, so they result in tau, and the non-computational state has a final outcome of 1. And because of that, this change of basis will not mix computational states with non-computational states. And the same is our R matrix. So it's going to be a 3 by 3 diagonal matrix if we write it in this basis. So what is the braiding operation B23 in terms of matrices? So what we see is that really what we're doing is first we apply the change of basis given by matrix F. Then we apply the braiding phase shift, which is the matrix R. And then we go back to the original basis, which is F inverse, or F inverse, which is equal to F. So B23 is equal to the product F, R, F, right? Or one of these could be interpreted as F inverse. Whereas the braiding 1, 2 is simply the matrix R. So these are two unitary 2 by 2 matrices if we view these operations as operations on a single qubit spanned by this 0 and this 1 state. There is one more braiding option that is available to us. We could braid the first and the third anyon in this triple. So this is the diagram for the braiding process B13. In order to compute the effect of B13 on our qubits, we can just apply the general braiding theory. This diagram shows that if we first apply a counterclockwise braiding of anyons 1 and 2, so which is B12 inverse, and then we apply the braiding of anyons 2 and 3, so this is B23. And finally, we apply the clockwise braiding of anyons 1 and 2. Then the overall composition gives us precisely the diagram for the braiding of anyons 1 and 3 in the clockwise way. So we can express this as that B13 is a product of B12 with B23 with B12 inverse. And now we can write down the braiding B13 in terms of matrices R and F. So B13 is the product of B12, which is R, B23, which is F, RF, and B12 inverse is R inverse. It turns out that our basic braiding operations, or these matrices R and F, RF, generate a discrete subgroup in U2, in the group of unitary matrices, which is dense in U2. So this means that an arbitrary matrix from U2 may be approximated as closely as we wish by iterated products of operators R and FRF and their inverses. This gives us a sufficient set of tools to implement single qubit operations. Dealing with 2 qubits and n qubits in general is more complicated in the setting of Fibonacci anyons, but nonetheless, the braiding operations that are available to us, again, will allow us to approximate as close as we wish arbitrary unitary matrices in those spaces. And let me reiterate the main point of topological quantum computing. The main point here is that these operations are topological in nature. It's only the topological class of the anyon exchange that matters here. And this means that this process is not sensitive to small deformations of these trajectories, and thus there will be no accumulation of errors when we perform topological quantum computations. In conclusion, let me point out that topological quantum computing has its origin and is closely connected to other important areas in mathematics and physics, to conformal field theory, to quantum groups, and to knot invariance. But these deep connections go beyond the scope of these lectures.